Hello! Hello and welcome to CSCI 1. My name is Lawton Nichols and you cannot see me right now, so let me start up my webcam so that I can at least show you my face once, just in case you never come to office hours. So, hello! Nice to meet all of you. This is my face. There is that. And go away, zoom. I am very angry because my computer died last time I was recording this lecture, and so I have to do it all over again, and I really hope everything goes alright this time. So this lecture is pretty much an intro one, and I'll introduce myself, we'll talk about the syllabus and stuff, and then we'll talk about the history of computer science, because this class is like half about computer science and then half about like philosophy. So we're like applying it to computer science. So you'll learn programming and then also stuff like ethics, which is really cool. And so that's the plan for today, and let's talk about me a little bit, and then I will move on. So, hi, my name is Lawton Nichols. I use he and him pronouns, and I am not full screen right now because I can draw with cool things, like they don't give you this fancy pen when you are full screen, when you're displaying the actual presentation. So that's fun. So I would prefer it if you called me Lawton, if you feel like it. It might be weird to call an instructor by the first name, but I would prefer it because I want to earn like your respect, right? I don't want to be given it. So if you feel like it, you can also call me Mr., you can call me Doctor, you can call me Professor, whatever you feel like it, but I would prefer it if you called me by my first name if you felt like that. So yeah, I went to Fresno State for my undergrad, so I know a little bit about the area, but I just graduated from UC Santa Barbara. That's where I went for grad school, and so this is my first semester here, and I've been teaching there, so I'm sorry if I say quarter all the time still. I'll get used to saying semester again. And yeah, outside of teaching, I do human things, and these are my beautiful moss balls, and hopefully once I get my first paycheck here, I can get a cat. I'm very excited about that. So yeah, thank you for putting up with me this semester. It's going to be weird. It's all online. I'm sure stuff that I have not planned for will happen. So yeah, we'll get through it together, you know? We'll make it work. So a little bit of info about the class. Because it's all asynchronous, I'll be recording everything. And then I'll try and like make a schedule. Like, this is my YouTube channel. I'm going to make the algorithm be nice to me and update all my videos at once. So the first lecture video of the week, we're going to pretend like this is a real class, right? So you're coming to class, in quotes, on Tuesdays and Thursdays, let's say. So that's when I'll have my first lecture video of the week up by Tuesdays or Thursdays at noon, so you can watch those anytime after that. But hopefully I'll try and make it record these early and give you guys more time to watch these things. Exams will be interesting because they're online. There's no real time for this class anymore. So I'll give you a 24-hour window, at least, to start and take the exams. But it will be like a real in-class exam in that it will be timed once you start it. So you'll have 24 hours to complete it. But as soon as you click go, the countdown starts. Okay? I hope that makes sense. Let's just make sure this is still recording. Yeah, we're good still. Nice. So that's that. Just quickly about expectations. This class is not hard. It's CSCI 1 after all. But the work may creep up on you if you don't keep up with it. So try and make sure you're doing all the work each week. Don't let it all pile up. So yeah, and programming, it's weird. I mean, I love it. I hope you'll love it after this class. But it's a different way of thinking, and that's something that I want you to embrace. But it might take a while to get there. So plan for your brain to feel bad, or plan for your head to hurt a little bit as you're learning this stuff. So there's that. And yeah, programming and writing is the two main parts of this class, and so you can't really get away with memorizing anything. Just a heads up if you're looking for like a super simple class. This is not the one. You will have to think a little bit in this class. And then I'm not trying to like scare you away. I want to to highlight the fact that I'm going to be here for you as much as I can. I'm going to have a bunch of office hours, and I hope you come to all of them. I will be here for you, and I will help you as much as I can, in person, in quotes, of course, or virtually if you ask a question on this tool called Piazza that I'll be talking about in just a second. So, what is this class about? Well, it's about a little bit of programming. We're going to learn to think computationally like a computer might do, and then we'll also hone our critical thinking skills, because that's very important, because these skills can be used to help with our programming. That's really nice. And yeah, we'll get into fun critical thinking topics. We will challenge our own beliefs about things, and we'll try to apply these all at the end of the day. These first few essays that I'll give you aren't particularly applied to computer science, more just your life, but we'll eventually start writing only about computer science topics. And so we'll talk about ethics. So what is good? What should we do? Like, is it okay to do things? That will come up a lot in this class. Okay, so that's that. And yeah, this class I would say is for everybody. If you just want a GE requirement, you're not looking to get into programming ever again, that's not an issue. Please stay in this class. I hope you enjoy it. And this class is built for pretty much anybody who wants to learn a little bit more about these topics. So if you just want to get credit for your GE, that's fine. I'm happy you're here. And then if you've taken programming classes already, or you plan on majoring in something like computer science, this class will help you with the bigger picture. Usually you have to wait until upper division to get into an ethics class in your particular field of science or engineering, but now you're getting one a bit early, so that's nice. So yeah, let's now quickly go to the syllabus. You might have been waiting for this. So here I am on the home page. If I go to the syllabus here, I can go and click it and open it. So let's just get to the stuff you care about. You can read the rest on your own. Boop, boop, boop. Textbook. So there is a required textbook, but that required is in quotes. The book will definitely help you when you're writing your essays and you're studying for the exams, and maybe just to understand the way I've been arranging this class is kind of in the order of some of the chapters. But you don't have to buy this book. I'm not going to force you to get it and ding you if you don't. But I think it could help you. So consider buying the book, or maybe wait a little bit and see if you need it. Something like that. So there's that. Dun dun dun. You'll be downloading stuff eventually. There'll be a midterm and a final. You'll be writing a bunch of essays. So yeah. As far as essays go, you're going to write 6,000 words in this class. It might seem like a lot, but we're going to spread them out. And then you'll also be doing a lot of programming assignments. The first kind of programming that you're going to do is in a language that is, it's called a block-based language. It's Scratch is the name of the programming language. And it'll look like this. You're going to use your mouse to configure these little blocks that fit together. And those blocks in order form your program. So this is, I don't know, the first one can be display image, and then this next one could be move that image, move image to the left maybe, and then all of this can be wrapped in another block, like a repeat block. Repeat. So this image just keeps on moving to the left and the left and the left forever and ever, something like that. So that's the kind of programming language we'll start out with. It's really cool. I hope you enjoy it. And then we'll get into a language called Python, which is you're pretty much writing in a text editor lines of code, something that might be more familiar to you if you've watched Hackers in the movies or something like that. But yeah, we're going to start off with Scratch because I think it's a bit easier to get our feet wet and not get too confused with installing all these weird programs and things. It's possible also that you have already taken CSCI 40 or above. And if you're interested in a challenge, these assignments might be a little too easy for you if you've already taken a programming class. So if you'd like a challenge, please come talk to me, come to my office hours or something, and we can get you assignments that are fun and doable, but at your level. Okay? So see me if you're interested in any of that. And then let's go to your grade breakdown, of course. So 30% of your grade, programming assignments. Another 30% written essays proportional to the word count of those essays. So for example, if you have a 250 word essay, that will be worth, if you have a 250 word essay and a 500 word essay, that 500 word essay is going to be worth twice as much as the 250 word essay. I hope that makes sense. And then we'll also have some weekly check-ins. So if we go to the course content, this first link is going to be your best friend. It's where the modules are for this class. If we go here, you will be completing a check-in survey pretty much every week. I think, yes, exactly every week. And that's how I'll be taking attendance. And so please make sure to complete that one, especially the first one on time, because I am required to drop you from this class if you do not do this first check-in survey. Okay, so that's that. Please check in with me every week like that. And yeah, then we'll have exams. 15% of your grade will be from the midterm, and the topics will be, of course, taken from stuff that you've been working on in like your writing assignments and your programming assignments. But of course, it'll be a little bit different because it's an exam. And then 20% of your grade will be from the final exam. Now, we'll get into the final exam in just a second. There will be extra credit, of course, at various points, and I will accept late programming assignments. So that's nice, but you will get half the credit if you submit late. But you can submit late up until the end of the semester. So if you have a really bad 2 weeks and you just have to work on another class for some reason, you can still come back and get half the credit and all the stuff. But if you turn in something 1 minute late, you just lost half the credit. So it's a bit of a balance, and I hope that you make sure that you stay on track. So there's that. I won't let you make up any of the essays late. Okay, so there's that. And then the final exam. So I have no idea about the final exam right now. TBD, and I can't select it for some reason. The issue here is the final exam schedule right now for the college is laid out in terms of the time at which the class takes place. This class, of course, has no time. So I'll still be figuring out when the final exam is, but I'll give you a 24-hour window again to take it. So we'll figure that out together. So that's that. Yeah, I think that's everything. Now, back to Canvas. So you'll be plopped at this home page, and you'll be working out of these modules, of course. Please look at all this stuff. Yeah, here are your 2 assignments for this first week. Your check-in survey, and the reason you're here is because you clicked this Lecture 1 link. It's all fun stuff. So just stay on track there. And all this stuff, these slides, these annotations, I will give all of this to you in addition to this video, of course. So don't feel like you have to write every little thing down. And yeah, all the exams and stuff, they'll be open book, because I'm not going to go and watch you work at your computer or something. That's impossible. So that's that. Instead of email, I would very much prefer it if you use Piazza. It's this wonderful, wonderful tool, and you can get to it through this link or through this link right here on the left side. It is a question and answer service, but it's also a private question and answer service at the same time. So you can ask public or private questions. You click new post, new question, post to just me. It'll look different for you, of course, but I'm the instructor. You can set the topics for your question, and it's beautiful because say it's 5 minutes before the deadline, you really need help, and I'm eating dinner or something, and I'm just not available because you waited too long. Well, you can post a public question, and your peers can actually go and answer that. So you guys can work together on answers, and then also collaborate and stuff like that. And then also I can go and answer a question myself, or say that yes, this student's answer was exactly the one that I would have put. I can say good answer instead of good note. Okay, so there'll be things like that. And then you can also, of course, post private questions to me. And so I encourage you to post a question publicly if you can. You can mark yourself anonymous on those public questions, but that will allow you to probably get an answer faster than just waiting for me. But yeah, please use Piazza instead of email. My inbox is ugly. There's a much better chance that I'll get back to you on time if you use Piazza. Okay? And yeah, just use your judgment. Please use public questions when you can, but don't share the answers to a midterm. or all of your code for an assignment. Something like that. Use your judgment. And then please come to office hours. So, home, office hours. You'll be clicking my Zoom link right here to join those office hours, and if something goes wrong, this is my ID and the password is CSCI, without the quotes. And so this is the times that I've currently blocked out for my office hours. Notice how they align with some of your due dates. I have tried very hard for that. Now, it's possible that I might have to rearrange these because of like mandatory instructor meetings, something like that, and I will let you know when that when that happens. Okay? And let's see here. Yeah, that's everything that I want to talk about there. Please come to office hours when you can. Yeah, and then please work on all this course stuff. Hopefully you'll be watching lecture 2 soon. So I think that's everything that I wanted to talk about for this stuff. So let me get out of here. For some reason I disabled my notifications, but still Firefox is sending them to me, so sorry about that. Let's talk about the history of computer science. Let's see where we are. 16 minutes recorded. Okay, so history of computer science. What's happening? Let's go back to the BC era. Let's go to 2700, 2300 BC. Well, okay, this is a bit odd, but it makes sense because a computer is just a tool that helps us perform computation, right? Computer, a tool that helps us perform computation, and so you can think of an abacus as like a primitive computation tool. I've heard that it's still big in Japan to teach students how to add and subtract. So you can add 2 numbers, you can subtract 2 numbers on an abacus. It's possible to multiply and divide, but it gets really weird. So yeah, we can think of an abacus as a primitive computer. So we were smart as humans way back then. And then let's fast forward a little bit. Let's get to the 1700s now. We're trying to do things a bit more formally. So we're going to talk about logic a lot in this class, and this is the beginnings of this topic called logic, and we will spend quite a bit of time on that. But we've also introduced the number system called binary at this point as well in time. So what is binary? Well, I'm glad you asked. It is, binary is a number system that is base 2. Okay, so base 2 we say. And the number system that we are familiar with right now is called base 10. Oops. Base 10, probably because we have 10 fingers. And so all of the digits in our numbers that we know and love are 0, 1, 2, all the way to 9. We have 10 digits total. That was a horrible little brace. There we go, that's beautiful. 10 digits total. And so once we get to 9, if we want to add one more, we have to use another place because we ran out of digits. Okay, so binary, base 2, that means that we only have 0 and 1 to work with, and that means once we get to 1, we immediately have to, once we add 1, it looks like 10 to us. It's 1, 0, and now that's 2. 1, 1 is 3. And so it goes in this way. And then you can also create a new a new number system that is more than base 10. You can have base 16, so you can have 16 digits, and now you have to start using letters, so that's fun. We may or may not get into that, but binary, that's what that is, and that allows us to think the way that a computer might think, so to think digitally, zeros and ones, high and low voltages. It'll all come together. So that's binary for us. And all of this history stuff, I'm not going to really test you on. You can always just, all the exams are going to be open notes, of course, and so you can just come right back to this if you ever need to. But yeah, this is more just to set the scene for you. So then we get into the 1800s, and now we are trying to use mechanical devices to perform computation for us. We input programs that say something like add x and y, and be take the square root of z, things like that, and add an x and y and store it into z, something like that. We're starting to write things that look a lot like programs, and people are inventing, Mr. Babbage here, is inventing devices that can perform general computation. So you have a problem, I can write a program and crank this machine until all of the little gears wind up enough to output the final answer. And be like, I don't know, show the value of z, something like that. That's like a program. Do this first thing, then do this second thing, then do this third thing. Charles Babbage only ended up writing or inventing a prototype for this analytical engine thing, which was supposed to be, which was supposed to perform like general purpose programs, or execute general purpose programs, but he never got to do it, the complete thing in his life. But this was still like the beginnings of programming and computers that are. It looks a whole lot like it does today, even. And then a little bit later, Ada Lovelace actually worked with Charles Babbage, and she was royalty. She was Countess of Lovelace, and so she was the world's first computer programmer, we say, because she was thinking about this analytical engine that Babbage was working on, and she came up with this algorithm. I don't know if you can see it, but you zoom in, it's like to calculate the Bernoulli numbers. And so that we consider to be the world's first computer algorithm, which is beautiful and cool. And if you want to look up Ada Lovelace, her life is really interesting. So she was like if you know from like English class, Lord Byron, she was the one legitimate child of Lord Byron and his wife. He had quite a few other children, but they were all illegitimate. So very interesting life for this woman, and she is the world's first computer programmer, which is a wonderful title to have. I want her life. So that's Ada Lovelace. And then a little bit later, the 1800s were popping in terms of computational techniques. So then we have Boolean algebra, named after George Boole. He noticed that, all right, we can associate 1 and 0, these binary numbers, with the concepts of true and false, and we can perform operations on these entities that we'll call true and false, which could be represented as 1s and 0s. And we can do fun stuff, like we can do the AND operation, and that gives us 1 back, or we could do like the XOR operation, and that also gives us 1, so let's make it 0. And these little operations, these Boolean operations, can be combined. I just want an excuse to use this pen. They can be combined to do arbitrarily complex computation, and that was the beauty of it. So this is a fancy diagram for a circuit that you will, by the end of this class, know exactly what it's doing. Isn't that cool? Okay, so that is Boolean algebra. We're starting to think about what 1s and 0s might look like, and some operations on 1s and 0s that do interesting things, like maybe add numbers or perform computation, just arbitrary computation. And then we get into the 1900s. This has all been done on paper, really, so far, and we've started to make little machines that, like, you've seen little cash registers probably. Back in the day, they had those that, like, take your money, show you how much, like, the price was, like, that's $10, please. And they had those little, like, I don't know what it even looks like, but little cranks that, like, you pull this lever down and then it adds these numbers, right? Something like that. Well, now we're starting to think about general purpose computation. Ada was thinking about it. Babbage was thinking about it. We can model computation mathematically in a very fun way, and Alan Turing was one of the first people who discovered how to model computation. And so we'll say that a Turing machine is a model of computation. So it's like a little device. It's a mathematical device that exists on paper, and it can go and execute any program known to man. Any program that any computer is capable of executing. Can be modeled in terms of a Turing machine. And I encourage you to look at the Wikipedia page for this. This is really cool stuff. Unless you get into upper division computer science, you probably won't learn a whole lot about it otherwise. And yeah, so the beauty of having a mathematical specification for a computer, or any possible computer that could ever be existed, because that's exactly what Alan Turing did, it has a lot of, you can start proving things. You can start proving things about these computers that could ever exist, and maybe talk about the things that they can do and the things that they can't ever do. And so a lot of cool proofs came out around this time, thanks to people like Alan Turing inventing these models of computation. So that's beautiful. I'm just going to geek out on the rest of this stuff, so don't mind me. And then in 1936, same year, we had the Germans, the German side, and we weren't very friendly with them. The UK, where Alan Turing is from, was not very friendly with them at the time, unfortunately. So we had the first digital computer ever invented. And so this is not mechanical anymore. Completely electric, no mechanical, no like moving parts. It's all just ones and zeros inside of electronics. It's using these things called vacuum tubes, which are huge. And so Z3, or I guess this was Germany, so it's something like Z3, was the first digital computer. And so digital means using zeros and ones. It's like the opposite of this word called analog. So digital, zeros and ones, on and off, true and false. These are all the same thing. That's what digital electronics mean. You're either in like a high voltage state, you got a 1 going, or you got a 0 going. And that computer, and all the computers of that era, took up giant rooms, or like warehouses. So like you got this giant room with your computer in it, and nobody's going to have one sitting in their lap for a whole, I don't know, quite a few years. And one of the reasons we have computers and phones and things that are tiny is because of the invention of this thing called the transistor. And this is probably, a lot of people say that this was the greatest invention of like the millennium because of this. So at Bell Labs, they were working to make better phones for some reason, and they came across the idea for this transistor. And what a transistor does is two things. One of those things is actually useful for our purposes. Can I get away from that? Okay, cool. So a transistor can amplify a signal, or it can function as a switch. And I don't need you to understand what these mean, but I'm going to give examples just in case you're interested. So you heard me say vacuum tube, and if you are a guitarist, you might know about tube amps. So here's your amp that you plug your fancy guitar into. Whee! And this is an electric guitar, by the way. Obviously, can't you tell by my drawing? But it has pickups. And the pickups have little magnets in them, of course, and your strings are made of metal, and so every time those vibrate, they cause a bit of magnetic flux inside of the guitar, or inside of the wiring of that guitar as it is like taken to the output device. So this wire is holding all of those changes in magnetic flux that can then be amplified, or that are like tiny little voltages that can then be amplified into sound from your Vox amp or something. Okay? And the idea is, the reason this is working is back in the day, these were made of like vacuum tubes, which were included in this Z3 for first digital computer. But an amplifier takes a signal, and it's tiny and weak because there's no electronics, there's no actual power coming from your guitar, but it takes that weak signal that holds the sound and it amplifies it. It makes it huge. So that's one really nice thing that a transistor can do, but we actually don't care about it in this class. We care about it switching things, so ones and zeros. So here is my little switch. I have a wire and right now it is unconnected, and then I need to figure out how to connect it by applying another line of electricity here. So if I apply enough electricity through this little input right here, it will cause the switch to go from the 0 state, to go from the off state to the on state, and start letting electrons flow that way. And so the fact that you can do this with a transistor allows you to do Boolean algebra. It allows you to perform arbitrary computation at a very microscopic level. And so you can think of transistors being smaller than human hairs. Those exist. That's what are in your phones and computers. So that is the idea. And I just got rid of that color, didn't I? Okay. So that's all I wanted to say about transistors. The fact that they can function as switches is the really cool bit here. And I just went off on a tangent. So now you know. And all right, now that we have computers and we can make them small, let's start making them talk to each other. In the 60s, in the late 60s, they introduced this thing called ARPANET, which was to share information across a bunch of different research institutes. One of them was the place I just graduated from, but I didn't take a networking class. Oh, goody. So that is the precursor to the internet, was the ARPANET, and now we have a whole lot more connections, I think you would say. And then into the 70s, in the more common era, people decided or realized that wouldn't it be nice if I had a computer in my house? That was not a normal thing to think back then, but it became a thing, obviously. And so one of the very first personal computers was the Apple I, invented by Steve Wozniak. And then that turned into a very, very successful company called Apple, helped a lot by Steve Jobs, his friend. So that is the history of computers in a nutshell. That was just more for your entertainment than something I'm going to test you on, but at least now you know where things are coming from and like where we've been. So I'm going to have a lot of fun editing this, but we are here. And so we talked about Ada, of course, but I didn't really highlight any other women, and so that's something I want to do right now, because computer science isn't just a bunch of dudes sitting around programming all day. There is a lot of women have made meaningful contributions, just as much as men. So here we have a few people that I want to talk about. So we have Grace Hopper first. So she created a programming language that I don't remember the name of, but that influenced a language called COBOL, which is very famous, which influenced a language called PLI or PL1, I can't remember, which influenced a language called C, which is still used today, for example, in the Linux kernel, which you go to a website, it's serving you that page on a Linux machine. It's beautiful. And anybody who wants to write any low-level software is going to use a programming language called C, and that language influenced a language called C++, which is used by a bunch of people in games, like Adobe uses it, Google uses it, and it's what we teach in CSCI 40. So there's that. So we have a lot to thank Grace Hopper for. Then Sophie Wilson, if you have a smartphone, like either an Android device or an Apple device, doesn't matter. The ARM architecture for CPUs was helped designed by her. So thank you, Sophie. And then there's also Shafi Goldwasser, who won the Turing Award, which is the equivalent in computer science of the Nobel Prize, and she earned it for her work in cryptography. And I was reading one of her papers on fully homomorphic encryption. It's a long word that I never usually say out loud, but I feel like that technology is going to change the world, probably. So she's done some really cool stuff. And then we have Margaret Hamilton, this is kind of like an iconic photo. She's standing next to all of the code printed out that her team helped to write. And so she helped get us to the moon. She worked on the Apollo program, and she led the team that produced the flight software for that. So thank you, Margaret. A lot of cool stuff built by a lot of cool women, and so I hope that helps to convince you that it's just not a bunch of dudes sitting around all day. Alright, we're back because I had to start up Firefox one more time to get ready for our next thing. So we were here, and the next thing that we're going to talk about is ethics. So what does it mean to do the right thing? Especially when these issues are hard to think about. So for example, I'm going to make you talk about this first one and this last one in your essay. Is it okay to steal to feed your family? Like, imagine you have no money, you have children, you've exhausted all your options, there's no charity, there's no church nearby, there's no nothing. The only option is for you to go and steal from some store to feed your family. Is that okay? And you could argue yes, or you could argue no, because there is no right answer for any of this stuff. But the one important thing, this thing that I added right here, is you'll be writing a bunch of arguments in this class, and we'll learn about what it means to be a good argument. And good has many ways of being described, like an argument. You can say that an argument is sound, you can say that it's valid, for example, and we'll learn about those topics and those terms. But yeah, I'm going to have you practice just knowing nothing about how to write a good argument, just knowing what's in your head, to try this stuff out. So I'll also make you think about this one. So is it right to kill one person if it means that you will save 50 people, and those other 50 people would die if you did not kill that one person? So that's really interesting to think about, I would say. So one argument is, no, I don't want any blood on my hands at all. I don't want to deal with that. The other is, well, yeah, 50 people. It's better that those people live, right? And 50 is more. Something like that. So I'll make you think about those and describe your thoughts. And then eventually in this class, what we're going to get to is questions that involve computer science and computers and their use. So, for example, governments have access to the infrastructure that we use to transmit information on the internet. Should they be allowed to look at the stuff that we do? Like, how much privacy should we have from our governments? And then also, like, it is the way that Google makes money, for example, is selling ads. So, and the way that it gets you to click on those ads is by tracking you all around the internet to discover the things that you're interested in. So is it okay for the websites that you visit to be tracking you in order to display to you more better ads, they say. So is that okay? And some people like have their entire their paycheck is dependent on this kind of stuff being allowed. So it's a very it's a bit of a gray area. All this stuff is a bit of a gray area, and we will talk about the tools to that exist in the world in terms of philosophy. We'll look at the ways that people approach these problems, and that's as good as we can do. At the end of the day, it comes down to you. What do you believe? So with that, let's get into your first assignment. So it's on Canvas. It's a mini essay. Take 250 words and respond to the following. So here it is. So you're going to talk about those two things. Is it okay to steal to feed your family? And is it right to kill somebody if it means that you're going to save 50 more? So please explain your answers as best as you can, and also you can talk about the gray area if you don't want to take a stance, but you have to talk about everything. You have to talk about the sides. Maybe it's okay to do something if something is true. Otherwise, it's not okay to do something like that. That's all very vague and weird, but that's kind of the space that you have to maneuver around when you're talking about these things. So talk about why you don't agree with the other side's argument. So if you're going to say, no, it's not okay to steal to feed your family, or yes, it is, you got to talk about the other side and why you don't agree with those arguments there. Okay? So there isn't a right answer, but you should give some good reasons and argue your points in a way that might convince me. Okay? So that's the idea. Even if I don't agree with you, of course, I'm going to give you perfect credit as long as you're doing this. And that's true for everything that you're going to write in this class. Okay? So good luck, and thank you for getting through this first lecture with me.